Um, welcome to all of you. I hope that uh, this is, everybody's been able to join and we've not had similar issues to the first couple webinars where people were struggling to get in. I want to start with a special acknowledgement and thanks to Joe Castiglione and to Zephyr for hosting this webinar for on behalf of TMIP. Zephyr provides, support to TMIP and was able to extend the use of their Zoom license so that we wouldn't be limited by the 100-person cap that we were on the first couple of uh, webinars. So. Um, uh, Today is the third uh, in our TMIP AI webinar series. Um, and our focus today is on AI in destination choice using the Reno case study. And Andrew Roan and I will be your presenters for today. Um, we always like to begin with a little disclaimer on behalf of Federal Highway that uh, the contents of the webinar don't constitute an official FHWA endorsement or recommendation, but really reflect the opinions of the presenters, Andrew and myself. Um, so in case there was any uh, confusion about that, I think everybody's familiar at this point. But um, as I imagine most of you who are on here are aware, um, we've had a couple of webinars already in the series. There was an introductory one a couple weeks ago. Um, and then last week we had a nice session um, focused on some simpler methods that have already been adopted in practice. Today, Andrew and I are going to be presenting um, the results of a lot of our work on that has taken place under this project for Federal Highway Administration that includes this webinar series as well as several other things. But we're going to be today presenting some of the main results of the research side of the project. Um, we're going to take a break then in July um, uh, and hopefully allow some folks to enjoy their summers. But we're going to reconvene in early August on the 5th. We're going to have a really great webinar, fourth webinar that will focus on TB ResNets and other ensembles of logit and neural networks. And our presenters for that will be Shinhao Wang from University of Florida and Sadhya Mishra from University of Memphis. And there will be several additional webinars in the remainder of August and September. And you can see some of the topics that we believe will be included that we're trying to finalize the speakers and the dates on. Um, so it's a little glimpse of what's coming. So with that, we'll go ahead and dive in. I'll provide a little bit of an overview of this project that we've been doing for the Travel Model Improvement Program at Federal Highway. The title of the project is Enhancing Travel Forecasting Practices and Effective Use of Travel Forecasts in Long-Range Transportation Planning through the application of artificial intelligence and big data. And there are really uh, four main or key elements of the project. The first was a review of the practice and literature. And the second was testing new methods that were identified as particularly promising in that literature review, and implementing uh, some of the most promising in pilot project and with a case study. And that is going, those two elements are basically what we're going to be presenting today. I'm going to be primarily presenting that first one, the literature review and the meta-analysis that we did in conjunction with that. And Andrew is going to be presenting most of the information on the case study, which we focused on Reno for. Um, we are working to incorporate the key kind of findings from all of this into playbook, which will be you can look for from Federal Highway later in the year. And of course, there's also the this webinar series, which obviously you're aware of, and we've I think hopefully I've advertised enough. So the focus of the project on the technical side is primarily on AI, but it's linked, AI and big data are importantly linked. Um, However, TMIP has conducted several projects and produced a number of resources on big data in the past. And so the focus here is a little bit more on AI. But it is inextricably tied up with big data as well. The intended focus of the project has been and is on practical improvements that can be hopefully brought to the practice in the near to midterm. And the thinking there is that in the mid to near term, which somebody asked in the first webinar, what does that mean? And I think I said maybe something like the next 5 years-ish. Uh, and in that time frame, we're probably not looking at uh, entirely new frameworks for travel models and travel forecasting, entirely new structures. Um, Rather, in this time frame, it's more likely, I think, and our focus has been on opportunities to either improve or replace individual model components. And one of the, and I'll explain this as we go, but one of the key technical methods there that for that we've identified are what are called AIDCM models, which are, we can consider as sort of an extension of the logit models that we all know and love, but incorporating also deep neural networks that have been so powerful in AI. And the focus in particular for this project has been on primarily, but not exclusively, on destination choice. And the reason for that is that destination choice is well known to be the largest source of error in all our existing models, whether trip-based or activity-based, and therefore also the largest opportunity for improvement. And so the hope is that we can ultimately realize or work towards realizing some of the really amazing kinds of gains that AI has achieved in other domains like computer vision and natural language. And you can see over on the right, just one little kind of motivation for this. This is real comparisons of the goodness of fit or the accuracy of some destination choice models. This is drawn from a widely cited paper from Nature on a neural network for destination choice called deep gravity. And you can see, I think for the last 20 years, 25 years, there's been a lot of interest and a lot of movement from gravity models of the original classic gravity models to logit destination choice models. And this result that they found is fairly typical. It's not at all uncommon for logit destination choice models to be able to perform twice as well, to have twice the accuracy and explanatory power of gravity models. But what is really remarkable, and they're part of the reason, again, that we've chosen to focus on destination choice in this project is our results exactly like the one in this graph, showing, the possibility of neural networks to outperform destination choice models by a factor of two or more in some cases. Um, so this is kind of a dramatic increase in the accuracy and the power of these models. So that was, part of the inspiration of what we're trying to do, what we've been trying to do in this project. So the first part of this, as I said, I cryptically referred to AI-DCM models, and that stands for artificial intelligence, discrete choice models. And really what they are combinations of neural networks and logit models. Um, and the motivation for doing that, for combining logit models and neural networks, is to try to get the best of both worlds, both to retain the theoretical basis and interpretability of traditional models in terms of the underlying um, traveler behavior, uh, while at the same time leveraging the predictive power and accuracy of some of these newer machine learning data science methods. There are a bunch of different ways that you can tie neural networks and logit models together structurally. And there have been a number of different architectures for doing this that have been proposed in the literature. Um, and I'm going to show you a couple here in a second, but we've particularly focused in this project on a structure or framework called TB-ResNets. Oops, sorry there. TB-ResNets are a relatively, simple and elegant structure that combine a logit model and a deep neural network in a simple parallel ensemble structure. Um, and structuring it in such a way that at the end, there's a softmax, which is basically kind of the logit function. And so the whole thing, can really be interpreted as a choice model. Essentially, you can consider the structure as, we have this ensemble model of the utility. Where, half of that ensemble is the traditional theory-based explicit uh, utility in the traditional logit framework, and the other half is a neural network, um, which is in itself can be very difficult, can be something a little bit of a black box and difficult to understand. But when we put them together, we can understand and interpret the implied behavior of the whole system, including the deep neural network, which could otherwise be something of a black box. And so also, part of the nice part of this is that uh, we can estimate the proper weighting of these two models, of the theory-based logit and the data-driven deep neural network, from the data itself. And in the published paper, the original Shenhouse's original paper, um, his focus was on mode choice. And he presented this really nice example of showing kind of the utility functions in terms of the trade-offs between travel time and bus fare, right? And on the left, you see the pure logit model, where we have kind of the perfectly rational trade-off of, for every minute of travel time saved, I'm willing to pay some fixed X additional fare, you know. Um, on the right side, you see the pure deep neural network. And that does not reflect any kind of rational trade-off, right, between time and cost. We wouldn't want to be basing our forecasts on something that looks like that. And there's a real danger of that were we to simply, grab deep neural networks and start, using them without really understanding them or having a framework like this for understanding them and the behavior that they represent and imply. But the TB ResNet combines, is a weighted combination of the pure logit model and the pure deep neural network. And in this example from the original paper for mode choice, um, the the data itself indicates that the best model is a mixture kind of like this one in the middle, close to this central one. And what we see here is something that's very plausible, right? That initially going from no cost to some cost, people don't like that, right? The utilities fall. But then if the bus fare is 50 cents or a buck or a buck 50, people don't really care, right? But if we keep increasing it to $2, 2.50, 3, people start to care again, right? And this kind of plateauing, this basically very nearly monotonically decreasing, but not necessarily linear kind of trade-off behavior or perfectly rational behavior is very plausible, right? And the ability by of this kind of structure, this TB resonant structure, to produce and this kind of behavior uh, allows it to actually fit the data better than either the pure um, Loja model or even a pure deep neural network that's not constrained in any way by any behavioral theory. So that was part of what we were really excited about and why we focused on TB resonance. Um, that is not to say, though, in any way that TB ResNets are the only AIDCM framework that is valid or helpful. And one of probably the other most interesting, architectures, AIDCM architectures that we identified from the literature review, but haven't had much chance to really explore beyond that as part of the project are called LMNL. And whereas the TB ResNet is basically a parallel ensemble of uh, for modeling utility, LMNL is basically a series, an ensemble in series, right? Where we decompose the systematic utility into the theory-based part and then a residual data-driven part. Um, the theory part, is the straightforward traditional logit structure, and the data-driven is less constrained neural network structure. And so this is also can be and may be a really helpful, powerful, and in some ways at a 30,000 foot theoretical level, very simple and elegant framework for combining logit models and uh, AI. So that is, the AIDCM models and frameworks. But even having identified that, there's a question of, well, what should that deep neural network look like, right? So for the TB ResNet, we've got the Logit model and the deep neural network ensembled together in parallel. But there's a wide variety of neural network architectures. So what should that neural network architecture look like? And we focused on what should that look like, particularly for destination choice, right? So we reviewed the literature on neural networks for destination choice, for spatial choice. We identified over 350 papers going all the way back to 1993, believe it or not, is when somebody first suggested predicting destination choices with a neural network. Um, uh, but there was very little and pretty much purely academic work up till 2015. But in 2015, there was a Kaggle competition that focused on destination choice for taxis and TNCs, right? Uber, Lyft, and that sort of thing. And that sparked an explosion of interest in this problem in the data science community. And so, following that 2015 Kaggle competition, there's this explosion of papers. It peaked in maybe 2020 and then has stabilized since. With this much literature, we had to prioritize, and we did that in a number of ways, but we also tried to understand, the real trajectories and development of literature. So we classified things a number of ways in terms of when the papers were published and what literature they cited, that they drew upon and were aware of, and the type of journal where they were published, whether it was a transportation journal, a geography journal, a data science journal, or something else in a few cases. The application, right, sometimes focused on all travel, looking, using GPS or LBS trace data, primarily. Sometimes was focused specifically on commuting, usually using administrative records. Sometimes was specifically focused on transit OD patterns and destination choice, usually using smart card data. Sometimes focused specifically on taxi, TNC, ride hailing destination choices. Like that Kaggle competition, and there are usually data sets very specific to that. But as time went on, increasingly also, there were oftentimes they're called social point of interest applications, but really, these are for location-based marketing. And they often draw upon location-based social network data. So could be things like Yelp, Foursquare, and so forth being used to, for instance, study and predict restaurant choice, destination choice. From this, we identified 8 main branches of the literature, but you can kind of see this here overall, a high level. There's a smattering of papers, the largest number of which were in the geography literature and some in transportation, in basically the 90s or just the beginning of the new millennium. And then things actually kind of quiet down, and there's not a whole lot of activity for a while until, like we said, things kind of explode after 2015. And since then, the vast majority of the literature are in data science journals, not in transportation or geography journals. So it's important that we, don't just limit ourselves to our traditional kind of favorite places. We're looking for, information. So uh, we identified, as I said, 8 different branches of the literature, and that was based really on their citations. Um, and you can kind of see this structure. There's the original stuff that's in blue, right? And then a few other different, branches of the literature that initially are completely unaware of each other, right? As far as we can tell. But then a couple of big branches of the literature, beginning in 2015, 2016. Uh, and eventually they begin to discover each other and cross-pollinate. But there are really distinct, these different branches of the literature explored really distinct neural network architectures and methods, right? So the original stuff was, focused on multi-layer perceptrons, right? Fully connected networks, very straightforward, right? But as different branches of literature came on, um, you get some of them looking a lot at convolutional neural networks. A lot of them looking at recurrent neural networks. Some of them looking at graph neural networks. Some of them really, trying to leverage attention mechanisms and or embeddings. And then, most recently leveraging transformers and generative AI methods. Oh, whoa, not sure how we wound up back there. Sorry. So, in order to, try to understand and really identify the most promising things, takeaways and directions for further study, we had to grapple with how do we compare these models. And one of the challenges is that people are using all different kinds of performance metrics, all different kinds of goodness of fit metrics and error metrics. You can see, over here on the right. But our assumption was, in order to make comparisons, that the relative improvement in fit or decrease in error are comparable. That doesn't mean exactly the same thing, but they, in some sense, are comparable, regardless of the specific metric that's used. And so we did a model-based meta-analysis based on that, um, and we fit a binary logit model for this kind of latent fitness score on a scale of 0 to 1. So sort of some kind of pseudo R squared type of metric. And we used the different types of architecture or methods for the neural networks as explanatory variables in this model. And we, used these squared errors with some regularization in order to estimate that. Um, we focused on normalized performance metrics, um, and especially ones that are on the unit interval already. And what we wound up with, 629 comparisons between different models, different model designs, published in 81 different papers that used 176 different data sets. And our meta model was performed very strongly, as you can see here, in terms of replicating the relative improvements of that are published in the papers. And what we found might not be entirely surprising, which was that generative AI methods were, far and away the strongest. And particularly by generative AI, referring really in this case to large language models that we're all familiar with from things like ChatGPT and Claude and such. And the other main generative AI methods are generative adversarial networks, which people might be a little bit less familiar with, or we call these oftentimes GANs. But these are the type of AI that's behind computer vision that allows you to unlock your iPhone and image generation that people are having lots of fun with. And in particular, the GANs performed the best. But several other methods did show some, significant benefit, including semi-supervised learning, oops, and graph convolutional neural networks. Um, you can see here kind of the top performing models and or papers, and the top six were all using a generative AI methods, and four out of the top five were GANs, were using generative adversarial networks. From that was our inspiration for trying to develop TB ResNets with a GAN neural network for the case study, and which we chose to do for Reno. And with that, I will turn things over to Andrew to talk about how this all worked. Do you want to share? Do you want me to stop sharing, or do you want me to just
I
advance
sent a
the link?
request to share.
Ah, okay. Let me
Oh, now I
stop
can do it.
sharing.
Okay.
Okay, there we go.
All right, so I'm going to talk about the Reno case study that we did. Um, for starters, let's talk about what the Reno model is, because I know all of you are experts on it, and I'm just going to rehash everything. The Reno model is an advanced hybrid trip-based model. About 500,000 people, 1,164 internal zones. It uses decision trees and boosting and trip generation, so it has some cool things going on in it, and some nested logit destination choice, which we'll talk about in a few minutes. It's a pretty neat model. Still a trip-based model though. So the data that we used to calibrate the model was primarily household survey data, just under 2,000 households and about 20,000 trips. To move forward with this case study, we also pulled connected vehicle traces, a total of 1.3 million trips or 1.4 million trips. That was before we panned down to just shopping and just social, recreational, and other trips. We did combine social, recreational, and other in the model to do this with against the connected vehicle traces because trying to determine what is social, recreational versus other in big data is that's pretty tough. So the training process, we started this out with retraining or re-estimating the destination choice models, and ultimately with both the Logit model, incorporating both survey and big data. So taking a look at both data sources as opposed to just survey data, and also using the minimum Wasserstein distance. And I'm going to talk about what that is in a few slides. We also trained a neural network, a GAN style neural network that uses, we kind of incorporated the survey data, but primarily big data, also using the minimum Wasserstein distance. And then ultimately, we wanted to estimate what delta should be or is with this, which we tried a couple different methods, but we're just going to show some examples of what it looks like under different deltas, different delta values. So the case study, I mentioned the two data sources, the 2,000 households from the survey and the 1.4 million connected vehicle trips. The two purposes, so home-based shopping and then home-based social, recreational, and other combined. And also looking at the both the log likelihood and the minimum Wasserstein distance as those metrics. On those two maps in the lower right portion of the slide, you can see, sort of where the survey trips were on the left and where the big data trips were on the right. Just to give you an idea of where, spatially where these things are at. So about that minimum Wasserstein distance. Um, so we're used to log likelihood. Also, there's a similar metric called cross entropy loss that's used in a lot of neural network training. And that's based on the likelihood of choosing the right zone or the right category, which is great, except when you're close and you have something where closeness matters. Um, so in a case of this, this test, the scenario down on the right hand side of the slide, we've got if we assume these are eight or nine zones where A is on the western side of a region and H is on the eastern side, you can see the orange model is over predicting A, and it's under predicting a couple others. Now the gray model is over predicting G, and both models are really under predicting H. So if A is on the western side of the region and G is on the eastern side of the region, both these have the same log likelihood, but that gray model is it's closer to where the real trips were going. And that's what the Wasserstein distance is. It's how close as opposed to just right or wrong. This is computationally intense, and it's really important that this is only done with things that are spatial. If this was foods, for example, the orange model could be over predicting apples, whereas the gray model could be over predicting guava, and both models are under predicting hamburgers. And that's, those don't offset. Guava is not close to hamburger, and it's not any closer than apple. So the nested logit models in the Reno model, they're nested based on districts, which you see on the right. And these districts are some of them are pretty large, particularly on the eastern side of the model, where there's not a lot going on. Much smaller in the internal portion, around where the airport is, downtown Reno. For those people who were at the Reno Applications Conference a number of years ago, there's a district just south of where it says downtown Reno. That's where the pepper mill is. So the process that we undertook, we estimated from big data. We called that model A. Then we estimated from the survey, and we called that model B, but we did that twice. One of them was we constrained the parameters that we could estimate from big data and let the estimation process figure out the stuff that we can't. So things that are, transit access, walk access, that you can't get from CV data. And then we also did another run. B2 is all parameters unconstrained. So we basically ignored, turned off things like transit access. I'm sorry, we didn't turn those off. We just let it figure it out. So it had transit access. It had less trips to go with, but created a model. And then we created weighted averages of B1 and B2 for the survey data. Estimation results, I am not going to drone on about that big table on the right. I'm just going to talk about what it means. Using maximum likelihood estimation, survey data, we were able to get to an R square of 0.24, which is pretty good. Using big data, almost as good at 0.2. The combination of the two comes out to 0.22, so pretty good. Using the normalized Wasserstein distance, we actually saw the shortest distance with big data, using the maximum likelihood estimation method. But the combined model is still better than survey data alone. Using the maximum Wasserstein or minimum Wasserstein distance as the estimation method, survey data and big data R squares were really pretty similar. 0.23, really 0.24. I mean 0.236 versus 0.241. Big data is almost the same, but we saw a much shorter normalized Wasserstein distance, indicating that the minimum Wasserstein distance estimation method should be closer, about 16% closer to the actual destination that was observed. Um, so some things we've noticed, and some of these are probably not groundbreaking. Survey data obviously supports things from the trip maker side that we don't have with connected vehicles. Impact of transit and walk access for travelers, um, travelers that don't have vehicles, by definition, they can't be in the connected vehicle data if they don't have a connected vehicle to use. Um, Now, we also notice those survey data because once you start chopping those, 20,000 trips down to, different purposes and everything, it has a lot of difficulty when you're trying to estimate things like district level effects, where, how many trips are going from one district to another and how important the districts are to the destination to the destination choice, as well as some more detailed things like malls. We couldn't really get to a significant number of trips going to malls with the survey data because, it's a portion of 20,000 trips. But when you have millions of trips, you start seeing, that malls are actually pretty important to use for a home-based shopping model. Um, when we put these together, the results just by itself there supports the value of trying to use both data types, both surveys and big data to estimate destination choice. Particularly when you're looking at 1,000 or more zones, or even 500 or more zones, and trying to get where the people are actually going and estimate good models. So this is kind of shifting gears into the Wasserstein GAN. Vince mentioned earlier, a GAN is a generative adversarial network. And what you have there is two competing neural networks. One of them is a generator, and it basically goes through and generates data. We fed it things like travel times, employment data, districts, and it would generate, utilities for outputs, for every zone. We would give that to a discriminator who would look at real data and compare the two. And both of these, both the generator and discriminator develop a loss output, which we used Wasserstein distance. We did some experiments with combinations of Wasserstein and cross entropy loss. Um, those loss values are back propagated through the networks, both of them. So there's actually two back propagations, and ideally, what happens is the generator is trying to fool the discriminator. Meanwhile, the discriminator is trying to get better at figuring out that the generator's not real data. So you've got this, that's why it's an adversarial network. They're both working against each other and they're both trying to be better than the other. But ultimately, that process comes out with a very powerful network, or very, very powerful neural network, because it was trying to be better, and that was the whole point of it. That's the point of a GAN. Um, Now there are challenges to training these things. Um, it's not as easy as simply taking scripts from GitHub and saying, "Let's put this in the model." Um, it, these, if you're used to a destination choice model or any choice model for that matter, we usually have things like, beta time, beta size, things like that. Um, that's not quite how these work. Ultimately, we feed these big arrays, big multi-dimensional arrays of data, that's not necessarily labeled. They are custom sized. So, the GAN that I built for Reno is based on 1,164 zones, based on their employment categories, based on districts, that are from their model. So I couldn't just take this GAN and put it in the model here in Cincinnati that's got 3 or 4 thousand zones in it and expect it to work. It would not. There's also a lot of hyperparameters to tune. Um, Part of it's architectural, how many inputs you're putting into the model and what those inputs are in real life, what they mean. The number of layers. So you see on the bottom right of the slide, there's two orange sets of dots, um, that represent the hidden layers. There can be any number of those, and that matters, as well as the size of them. Do you have, 100 inputs going down to five layers, to five layers of five, or do you have 100 going to one layer of 10? That that determines how the model works and how the model works through everything from input to output to determine, what the output's going to be. There's things like learning rates, how much the backpropagation can adjust various things inside the model. Inside these are a lot of numbers of weights and biases and various factors that are used to get from the input to the output. And you can set how much it can learn each time, each training iteration. There's things like dropout, which turns off certain neurons to make sure that they are significant, or to drop them if they're not significant. Batch size matters, and that's kind of a funny one because you the server I was using to train these models can fit the entire model in training, in one fell swoop, the entire batch of data. And that's not a good idea because you want to see some of that variation and some of the things that happen with smaller bits of training, and it actually helps it train faster. I actually did one or two runs with, batch sizes. I'm just going to call it infinite, basically everything. And it took longer to train, and it didn't actually train as well as using smaller batch sizes. And then there's even more things, activation functions, optimizers, and gradient norm clipping that control how the model can work together, internally to basically adjust and avoid things like overfitting, avoid things like exploding gradients where you have something weird going on that's causing crazy results. The hyperparameters that we ultimately settled on, this was after probably I was hitting close to 500 different training runs for shopping, and just over 100 for social rec and other. Needless to say, shopping was the one where I was doing all my testing. I found that a batch size of 32 worked with this data. That is definitely not a recommendation of where somebody should say, oh, we should use 32 on if we're doing this. Um, might work as a start for a thousand zone model. But definitely it's something that I had to tune, and I had many, many logs of different batch sizes, different depths of the hidden layers, different sizes of hidden layers. And that's one that, the depth and hidden layer size definitely was different between these two purposes. Whereas dropout, the learning rates for both the generator and the discriminator, the adversarial loss, and the sinkhorn distance, all seem to be more related to the model size as opposed to the content of the purposes. So, in terms of challenges, yeah, I mentioned that you can't just take a script and use it. There's all these knobs to mess with. Um, you run this and you get a model that maybe says it's good because it's got a great loss rate, or the cross entropy loss looks good, or even I was actually calculating log likelihood that it would say it was good. Um, I would ultimately take the best looking models and run those through another script that would look at the trip length frequency distribution and district to district flows. And I had two logs. One of them is a website called W Weights and Biases, WANDB.com. The other one's a simple Excel file where I was tracking things like the coincidence ratio, because I was looking at things like the trip length frequency and comparing what the GAN said versus our holdout sample, and how did it look? And I had some that they had coincidence ratios down in the 30s and some that were up in the 90s. And in addition, looked at the district flows and used that to determine, should I turn on an intrazonal factor to look at to try and adjust for intrazonals, or an intra-district factor to try and allow some adjustment of the model for things like that. But this is really important to make sure you do this ground check to make sure that the GAN who says it's doing good is actually good. And then there's at the bottom there's the little gotchas, the things that would sometimes frustrate me in the middle of a day. Um, One of them is PyTorch has some ways that it expects to work, and it tracks a lot of things behind the scenes. There's various tensors that it tracks, and one of them that I saw in various forum posts, as well as the chat GPTs and everything. You have to make sure you're not doubling up on loss functions and running the loss function twice, because it actually tracks that, and you could cause problems in how the model updates itself during backpropagation if you do it wrong. And it's pretty easy to do it wrong because it we might not think of how it works internally, just because it's not something that's very common with us yet in this industry. Another one is device drivers delivered by Windows updates. I think I had to rebuild my Python environment 5 times because of the video card driver on the server. Windows update would deliver it, and all of a sudden nothing works. So, shifting gears to the implementation and how it works inside their model. Um, I tried to make it as easy as possible, mostly to protect everyone's sanity, including my own. There is a checkbox that I added. So in the upper window there where it says destination choice, I don't know if I actually have a pointer on this. Um, there's everything above the box that says globally turn on or off TB resonance was already there. So that was, the destination choice size terms, attraction rates, and shadow prices that were already set up in the model. I added the checkbox and a control file, and I ultimately added the location of the Python executable to make sure that Transcat was using the right one. The control file is just a simple table, basically the purpose, which matches the purpose codes that we're using in the model. The delta value, which is anywhere from 0 to 1. 0 basically means that it's, it'll run the TB resonance model, but not actually do anything. And I did test that to make sure that the results were consistent, between the two, between on and off. And then the paths to the model file and parameter file. The model file is basically all those weights and biases that go behind the scenes for the neural network model to work. The model setup file is just a handful of parameters that define the object that holds that. For whatever reason, I have to define the object and then load it with data. So, and if you try and load that data into an object that's not correctly sized, it'll throw an error. We did use a handful of Python libraries. Most of them are fairly standard, with the exception of PyTorch, and I mean CaliperPy is standard if you use Transcad. PyTorch is not one that we've worked with a whole lot, and as an industry. Most of you, if you've been around for a while, have probably heard of and probably used Pandas and NumPy if you use Python. And then there's some built-in libraries that I use, like the OS library, one of the best libraries out there. And then, of course, when it calls Python, Python reads the PT file, the best underscore model PT, as well as that model setup YAML file, so that PyTorch can work. So the good news is, after doing all this work, we were able to achieve some pretty good accuracy gains, similar to what the published literature says. This is based on a 20% holdout sample, and it may have actually been 40% for social, recreational, and other, because we had a lot more observations from the CV data for that purpose. But you can see, in terms of row square, we basically doubled shopping, and then for social, recreational, and other, over tripled the row square. So some really good output metrics according to the test data. And of course, we were able to implement this and run it as part of the regional model. Now, everyone knows that if we have a slide that says the good news, it's going to be followed up with one that says the bad news. Um, when we started doing this in the model, we were unable to see some of these gains. We saw initially some weird stuff, and I'll talk about some of that because it was a learning opportunity. But there was also maybe a situation where we were putting what we think is an F1 engine and maybe a nice sedan. And I drive a sedan. I don't know what an F1 engine would do to it, but I'm sure it would not like the transmission. Probably not the tires either. Um, we noticed some of the inputs were pretty different between the connected vehicle data and the regional model data. Um, there's it, this is one of those times what's right, what's wrong, because the connected vehicle data could be wrong. It could be more right. It could be missing something because it's connected vehicle data. So there's a lot of questions there. Um, the GAN could reflect some of those idiosyncrasies. In fact, it probably does. There's questions about, or do we have something going on in the regional model that we need to take a look at? And some of it, related to activity scheduling and, if we made some changes to things like, activity and trip generation scheduling, could we improve it? Both improve the regional model and the GAN itself. Which probably. So in terms of the differences we saw, the leftmost map is the weighted survey, the middle map is the unweighted survey, and the map on the right is the connected vehicle data. And there's some pretty obvious differences. With the shopping data, you can see a lot more productions in sort of the north and south portions of the region. um, the survey's almost missing one zone. You can see like there's one around the airport where there's much fewer productions than the CV data. And I will note we do adjust the CV data for things like rental cars. We try to pull those out, and we have some methods to do that. So that was one of those things where we tried to adjust for it, and I think we pretty well did, but there's definitely some differences in this data, and we might be seeing some of these. When we look at social rec and other, same arrangement of maps, but you can see there's a lot more trips, particularly on that eastern fringe of the model, kind of going off screen there. There's a lot more there that's coming in, and there's some other stark differences. Oddly enough, there's fewer trips coming out of the airport. And even there's a zone north of it that there's far fewer trips compared to the survey. So these are definitely two different data sets. In fact, the correlation, if we look at a district to district flow, is about 50%. Spatially, we took a look at how the data kind of looked with in terms of where destinations were, because that's pretty important with a destination choice model. And just trying to determine what is significant and what isn't. When you have millions of trips, we said, well, significance 50 or more big data observations. Surveys, since we don't have as many trips, we said one or more is significant. And you can see with shopping, there's two places where one says it's significant and the other says it isn't, and those are sort of concerning. But for the most part, shopping we were close. A lot of places where we didn't see things as being real significant. Social rec and other though was a different story. Still a lot of places where there's an offset between one says it's significant, one says it isn't. Um, you a decent bit of place of agreement though, but still, I mean, not really agreeing too well. And looking at district level correlations, you know, unweighted survey versus weighted survey and versus CV data, some of these R squares are not great. Correlation of 0.62 or even zero point 0.4, unweighted survey versus I think that's CV data. That we've taken a look at a lot of data and that was pretty concerning. We also saw some temporal differences. So, shopping, you can see, survey 5% of trips were shopping trips there. Or 5% of the shopping trips were during the AM period, whereas three times as many in the CV data. So we're seeing, still the majority in the midday, but there's a big difference there with the AM. It could be people stopping for coffee on the way to work, which is one of those things that's commonly missed by it in a survey response, but commonly hit with CV data that says, "Oh, you stopped somewhere for 2 minutes, therefore it's a stop." And yes, I simplified that a little bit, but you know, I I think we all get the idea. Social Rec Other is a little bit better in terms of agreement. Survey had a little bit more stops during the midday, your trips during the midday versus the CV data, but they largely agree. So we did notice, we accidentally found out that how sensitive the GAN is to travel time. Initially, when I set out to do this, we had a matrix of here network travel times that we had used with some of the initial estimations with this model, and we started seeing in the applied model, the GAN model, and this is with 100% of the GAN being used, not using the TB resonance approach. And we saw 40,000 trips going to this particular zone highlighted in red. To give you an idea, it's about 10 miles from the sort of southern-ish area where you see some development to the northern part of that, or northwestern part. So this zone is huge. There's not a lot going on in it. There's some stuff going on down in the southern portion of this zone, but a large part of it is vacant or other uses that are low intensity, very low intensity uses. Um, so the here network travel times were 90 minutes to get probably to the middle of that zone. Probably using a bunch of miles of dirt roads that may or may not have been the most efficient way to get from one side to the other. Whereas when we applied this in a model, their model looks at the development at the edge of the zone, where the development is, and it's about 35 minutes from downtown Reno versus about 90 minutes with here. The GAN, as it saw that and weighted everything through with the weights and biases, it put a ton of trips out there. We ultimately had to retrain the GAN using the model as the travel time source, and it did a lot better once we fixed it. But that's one of those things where you know I'm not trying to rip on here as a data source or question the model here. It's they're looking at two different things. Here was definitely looking at more of a geographic center of the zone where like I said, you have to use miles of dirt roads to get there, whereas the model is using something a little bit more a little bit more what we're used to. And I think the standard modeling practice would have been to put the centroid connector and about where the development is, which is a lot closer to paved roads. Um, let's see, TB ResNet. So regardless of the data set, um, putting the data together, both the GAN and the Logit model, always outperformed one or the other. And I'm going to show some examples of this. But the deltas really matter here, and it allows for some interpretation of what's going on with both travel time and behavior and how the model ultimately works. Um, we'll see that the logit model is pretty simple. The GAN model is pretty variable, has a lot of variance in the data. But in between those two extremes, it actually looks a lot better. And this is the utility versus the travel time. Um, The reason why it's so light is because we have an opacity so that as we see these going through, you'll see where the trends develop. But if you look close enough, you can see that there's some utilities, positive utilities over 5 utiles, particularly for some of the short trips. There's also some really negative ones, some down almost to -20. And for short trips, that there's what looks like -20 or 1, unless that's a blip on my monitor, but there's 3 trips in that -15 to -20, 0 to 5 minute box. That's a pretty big disincentive for such a short trip. Now, if we add in 20% of the logit model, so this is 80% of the GAN model and 20% of the logit model, we start seeing those pull in. There's no trips now down and like down below -15 utiles. There's no trips above 5 utiles, and we're starting to see that they're starting to come together, and you start to see that general trend that we would expect to see where, as trips get longer, it becomes we have a lower utility. If we go 60/40, so 60% GAN, 40% of logit model, we're starting to see it pulling in more. We have seriously negative utilities are starting to go up, and they're starting to get more towards, what we would kind of expect to see. We're seeing the variance tighten up with this whole scatter plot. And we're seeing the positive values. Now there's none that are more positive than 5. And particularly, we're starting to see that a lot of like that 5 to 10 and 10 to 15 range are becoming less and less positive. And as we go in, this is 40% GAN, 60% logit model. We're starting to see even less variance. So we're starting to see it tighten up a lot more in terms of, what that utility is versus the travel time. 20% GAN, 80% logit model. It's really tight now. You can see that there's definitely a line developing there. And then when we get to just the logit model, 0% GAN, 100% logit model, it's basically 2 lines. The sparse line there is downtown Reno residents, and the other line is everyone else. And when we put all these, this is basically all of them stacked. You can kind of come to the conclusion that the 100% GAN is probably not the best approach. Just too much variability, too many wild things going on. And, if we're seeing wild things with travel time and utility, we're going to see wild things going on in the assignment. The line, 0% GAN and 100% logit is very strict. There's probably more variation going on in actual household travel than what that line suggests. So, as with many things, the answer is somewhere in the middle. So, with that, I'll throw it back over to Vince for summary and conclusions.
Thanks, Andrew. Um, are you just gonna advance the slides or
Sure, I can advance them.
okay, great. So, uh again, to sort of recap and try to distill some of what all we learned from, over the course of this project, and especially uh, the um, uh, the Reno application case study. There's several things. One, I think so we learned a couple of important and exciting things from the literature, right? Um, and one being the probably one of the really exciting things being that deep neural networks trained on big data can predict destination choices much more accurately than logit models. And we identified GANs in particular as the best performing um, uh, neural network architecture or approach. We also identified AIDCM frameworks like TB resonance that were able to combine logit models and neural networks in ways that preserve the behavioral interpretability of traditional methods. And I think this is really important um, for us to be able to explain and defend our models in terms of what they are doing to, to the general public, to elected officials, and also to defend it in court against, NEPA challenges and things like that. So, in terms of, you know, then what worked, again, kind of reiterating Andrew's good news, we were the publications that were showing these massive improvements in model accuracy from neural networks like GANs versus over traditional methods like logit models. Um, are not all hype. We are able to reproduce this with real the real, big not Foursquare, Yelp, but the kinds of big data that we have available to us in our profession. And we're able to to achieve similarly impressive gains over even very good logit destination choice models, improvements in accuracy of, 2x, 3x, 3.5x, um, really substantial kinds of improvements. Um, uh, we also, were able to demonstrate, apply the TB-ResNet methodology to combine those GANs with the logit models. Um, uh, and that did even better. That those combinations, those mixed models between the pure logit and pure neural networks or pure GANs, always improved better, always than one or the other, and always resulted in at least some additional gain in accuracy. But probably even more important than that accuracy gain was that they resulted in more plausible behavioral implications, right? So what Andrew was just showing you there with the utilities related to time, essentially you can understand that as you're looking at essentially a value of time distribution, right? And in the logit model, you're essentially there were basically like, right, just oh, essentially two values of time, right, for the downtown residents and for everybody else in the region in Reno. Whereas, the GANs, it's a distributed value of time, but the pure GAN is really widely distributed, right? And there's some pretty extreme values there, right? Whereas the TB resnets that combine them produce, distributed values of time that look more plausible than either, the pure logit or the pure GAN, right? So we're able to, both of, kind of those first two key findings from the literature, we were able to validate or verify to some degree, in Reno with, the kinds of data that we really have available. We're also able to uh, fully implement this, and actually, run a model in Transcad with these advanced kinds of AI neural network methods. And that's, kind of a first. And we also, it maybe, I don't know if this is a footnote. I think it's a little bit more than a footnote, but we also did, kind of as a byproduct of this, we did produce improved logit destination choice models. Both by estimating the logit destination choice models from the combination of survey data and big data, right? So we're able to on the one hand, incorporate variables related to the trip makers themselves from the survey data that you can't get from the big data. But we're also, the big data was able to support much more uh, uh, stable and significant results, in terms of, spatial district level effects and so forth. The minimum Wasserstein distance estimation also improved the spatial goodness of fit. Measure if we accept that being closer is better than being further away, right? We were producing logit destination choice models that are, roughly 15% closer to, their predictions were roughly 15% closer to the actual observed, destinations than the traditional maximum likelihood estimated logit models. And the decrease in the traditional metric, the rho squared from the log likelihoods, was only about a decrease of 1%, right? So we got 15% closer for being maybe 1% less exactly right. So that, I think all of these things, are some exciting things that have come from this project. But again, trying to be balanced and completely transparent. Uh, you know, um, I had hoped that this would, we could be with you today and just present this glowing, overwhelming, unqualified success. But the reality is some things didn't go as we hoped, and even though in the model estimation, the model training, we were able to see these huge gains in accuracy. Um, uh, we weren't able to translate those into similar kinds of improvements in accuracy in the ultimate uh, traffic volumes uh, produced by the model, which was frustrating and disappointing. And we really had to think about why that was. And what we have figured out, the best that we've figured out, is that the root cause or causes is really probably a combination of two kind of interrelated issues, right? But the fundamentally, what a bunch of things point to is the mismatch between the inputs to destination choice, that the GAN was trained on from the, CV data, connected vehicle data, and the inputs that it was then applied to that came out of the upstream model components of the regional model, which are all based entirely on the survey. Um, uh, which raises the question, well, which is right? Is kind of is the connected vehicle data right? Is the survey right? Almost certainly, though, and we can point to specific reasons. Neither of them is, it's not a question of one is right and the other is wrong. Almost both of the data sets have biases, and there's pretty strong evidence of that. But we should be able, to um, actually translate some of those gains in being able to reproduce the origin destination patterns into actual travel volume forecasts. But that's going to take more work. And there's probably at least three different ways, avenues to pursue for that in future work. One is exploring different GAN architectures and training strategies that might produce more robust GANs that aren't quite as fragile, that are able to deal with um, uh, differences in the inputs a little bit more realistically. That are maybe, the sensitivities are a little less wild, right? Those distributions are a little less variable, right? So that's one possible avenue for, future further work. Another is better data and or better data reconciliation, data fusion, right? We really kind of didn't try to fuse the survey data and the big data in this case. We just kind of respected them each as their own things. Didn't try to reconcile them or come up with what we really thought was the truth between them in this case. And maybe doing that would allow us to, produce a stronger model in the final practice in terms of the accuracy of those traffic flows. And the third option is that, we might just need better upstream model components, right? Although as much as we would like to just be able to swap out one component like destination choice, there can be potential problems like Andrew's example of putting the race car engine in your family sedan, right? That doesn't necessarily that can cause real problems, right? We might in fact have to make improvements to other parts of the overall vehicle, over other parts of the model system in order to get to really realize the full potential. So, in terms of the final kind of takeaways or conclusions, one is I think we should all be aware that there are that survey data and big data are different and different in some ways that are can be in some cases subtle and complex. And it's not a simple matter of one being right and the other being wrong. It's not it's almost certainly a question of there being things wrong in both of them and trying to figure out which, where the truth lies between them. One of the nice things about, a nice takeaway too, though, from this is that I know for myself, I come away with a new appreciation, a new respect for our old logit models, our traditional methods. They're really is um, the logit models not only are better grounded in behavioral theory, but they also produce more robust models that aren't so that can don't require really accurate, nuanced inputs. We also, are able to there are real opportunities for improving our traditional logit destination choice models. Several of them, one being, to estimate them from both survey data and big data. Also improvements to the model specifications like nesting, like using nested logit over just simple multinomial logit, and also estimation methods like minimum Wasserstein distance rather than maximum likelihood. Um, that we should as exciting as the AI stuff is, this has been a reminder for me of the real power and value of our traditional methods. And lastly, regarding the AI, there's a tension. On the one hand, these some of these methods can, we've further, verified, validated that they can produce huge accuracy gains under very careful conditions, right? But they're very powerful, but they're also can be really fragile. They can be very sensitive to inputs. I mean, one way that we could, maybe we encapsulate this takeaway is to say, better models require better inputs, which makes sense, but is challenging. Uh, and so ultimately realizing some of the promise of these powerful methods will require more work. But I see the Reno case study, not as a cautionary tale, but rather as an exciting second chapter in an unfolding story, right? I think, the academic research that we see, that we reviewed in literature, I think provides kind of this first chapter of what's possible. In this chapter, we are able to see, to some extent, verify that, yeah, some of that really is possible, but at the same time, wow, it's not so easy as we might have been tempted to hope. So, where do we go from here? I think it's up. There's an uphill climb that is challenging, but at the same time, I think promises um, leading us to a summit that is well above, any heights that we have been able to reach in the past. So I know we've unfortunately kind of run up against our time. There weren't a whole, and so I don't have a hard stop, and so maybe Andrew and I can hang on here for a couple minutes to try to answer a few questions. We can certainly, please, we'll be happy to follow up if you want to email us, though, with further questions. I did see, there was a good question from Cara early on about, wouldn't this be even better, in the context of a tour-based or activity-based model framework? And I think that part of what we saw, in terms of the need for better input distributions, may be right. Uh, but I think I'd say stay tuned for webinar number 4 on August 5th. Sabia, I think some of Sabia's research that he's going to present will be relevant there, and you'll see an applicant. He has been looking more at activity scheduling in more of an activity-based kind of setting or framework or whatnot. So for those of you who are itching to see, okay, how does this apply an activity-based kind of more of an activity-based framework? Stay tuned for the next webinar. Um, uh, so uh, I've been focused here. Andrew, I know there have been a couple other questions. Um, uh, One of them was about how and why we experimented with combinations of cross entropy loss or traditional log likelihood or whatnot, and Wasserstein or Sinkhorn distance. So I don't know if you want to just briefly, respond to that.
Yeah, so the Sinkhorn loss is one that has some parameters involved in it. So that was one of the reasons there was a little bit of instability with the wrong parameters. Another one is I actually observed some odd effects of using the Wasserstein distance by itself in a couple of situations, and ultimately mixed it with the cross entropy loss to just try and make that adjustment and make the model train faster as well as better. So, and I'm going to go up. You started sort of right in the middle after other people added questions. Let's see. Zhao Li, for the travel demand model components like trip generation or destination choice, the outcomes are usually unbalanced, especially for rare cases. Only a few households generate 10 trips. Some TAZs may get only several trips. Machine learning models prefer to ignore these unbalanced rare outcomes when optimizing overall accuracy. How would you address this unbalanced rare outcomes in the input data? Um, I didn't really push to address those in terms of, if there was a TAZ that only received one destination, even with millions of trips, when you start slicing and dicing by 1000 by 1000 matrix, you don't get a whole lot of situations where you can see, that level of granularity. But that's also a good reason to not go directly with a GAN and to mix it in the TB resonance situation, because then you're using the model, a logit model to meter that and to improve that. And that's really part of, the weakness of one becomes the strength of the other sometimes. And that's one of those situations where you're definitely seeing that.
Yeah.
Um,
Um, Marty, asked about, well, rather than just using kind of the more or less pure big data from the connected vehicles, would it be helpful if we tried to, use information from traffic counts, right, to improve the OD patterns? Through ODME or various kinds of data fusion. And absolutely, right? I think that's one of I think the three kind of promising avenues for further work, that might allow us to kind of bring, realize more of those gains that we're able to get, purely with the big data, and translate them into what we're interested in terms of traffic volumes and transit ridership and so forth. And so yeah, I absolutely think that's one of the promising kind of few directions for future work. Um, uh, and Sherry asked Andrew about the run times for the training of the model.
um, with only cross entropy loss, it was about an hour per purpose. When we started adding in the Sinkhorn approximation of the minimum Wasserstein distance, that at times was taken up to 12 hours per purpose per full run. So all iterations to the end.
Yeah. So this can be
So
computationally intense, but that's for the development of the models, the training or the estimation. The application of the models is lightning fast, right?
yeah, I mean, it was maybe on the application side, maybe 15 minutes longer, and that's four iterations. So, a few minutes per iteration.
Yeah, yeah, exactly.
Moving up in the list, Pedro Donoso, have you tested the sensitivity of the models in different scenarios? We have not. That was one of the things we actually have wanted to do because we obviously have concerns, and I've done presentations in the past on actually doing sensitivity testing with other models. So that was one thing I wanted to do with this one, and we just ran out of time.
Well, I know we're over, so we want to respect people's time. Some really good questions there. Again, our emails are up there, and Andrew and I are both happy to follow up with people if there are more questions. Obviously, this is a lot of information, a lot of exciting and complex things to continue to kind of think about and work on. So. Anyway, I hope that you've enjoyed webinar number 3. Again, we're going to take a break. Enjoy your July, and hopefully you can come back and join us again in August for webinar number 4. Thank you all so much and have a great rest of your day.